space and time is just a membrane floating through the multiverse. Another, called quantum loop gravity, suggests that nothing really exists at all, and that everything is ultimately made up of tiny loops in space and time themselves. But despite gravity's unwillingness to fit in with quantum theory, I believe there's something worse lurking in the quantum shadows, something truly nightmarish. Late into the night at physics conferences all over the world, over drinks at the bar when we scientists huddle together to debate and discuss our strangest ideas and dreams, there are still things that really, really bother us. And chief among these are the quantum mechanical laws that atoms obey. And in particular, one aspect of these laws, something called the measurement problem. If you want to see fear in a quantum physicist's eyes, just mention the words, the measurement problem. The measurement problem is this: an atom only appears in a particular place if you measure it. In other words, an atom is spread out all over the place until a conscious observer decides to look at it. So the act of measurement or observation creates the entire universe. And just to show you how mad this idea is, I'm going to explain one of the most famous hypothetical experiments in the whole of science. It's called the Schrodinger's cat experiment. Erwin Schrödinger was one of the founding fathers of atomic theory, and in the mid-1930s devised a thought experiment purely to highlight the absurdity of quantum mechanics. He suggested you take a box in which you place an unopened container of cyanide connected to a radiation detector and some radioactive material. Now the idea is that if an atom in the material emits a particle, this will be picked up by the detector, which in turn releases the cyanide. Next you take Schrödinger's cat, which in this case is a lovely Norwegian forest cat called Dawkins. Now I should point out that this isn't real cyanide. You place the cat in the box, you close the lid, and wait. So here's the conundrum. According to traditional quantum mechanics, known as the Copenhagen interpretation, all the time the box is closed, the radioactive atom inside has yet to make up its mind whether it has decayed and spat out a particle. So we have to describe it as both having decayed and not decayed at the same time. Think about what this means. Since the radioactive particle triggers the release of the poison, the cat is both poisoned and not poisoned. So until we open the lid to check up on the fate of the cat, what's called making a measurement, it's not just that we don't know, but that the cat is literally both dead and alive at the same time. This is clearly a paradox, or is it? The paradox of Schrödinger's cat and the contradictory nature of the measurement problem really does force us to accept that tiny objects down at the atomic scale obey their own set of profoundly strange rules. But at larger scales, those of everyday human experience, those rules vanish, and an utterly new set of nice, intuitive rules take over. How can this be? Some argue that in fact the quantum weirdness of the atom might actually be writ large across the cosmos, that we may have to rethink everything we knew about the universe. Welcome to the many worlds interpretation of quantum mechanics and its chief adherent, David Deutsch of Oxford University. Deutsch proposes that reality itself is profoundly misunderstood. He says that what quantum mechanics actually describes is not one universe, but an infinite number of parallel universes. He calls it a multiverse, in which every possible quantum mechanical outcome for each and every atom in the universe exists somewhere.
So an atom and its electron are multiversal objects, and that multiversal object is what the quantum mechanics is describing. Now, that means that the parallel universe aspect of reality as described by quantum theory must apply to objects of all sizes: humans, stars, galaxies, everything. And that's why we call it the parallel universe theory rather than just parallel electrons theory.
Because we ourselves are made of atoms, after all.
We are, that's right. And the same theory that says that the atoms exist in more than one place in different universes says that we humans also exist in more than one place and in more than one state of mind and so forth in different universes. And there are some universes in which you and I don't exist at all.
The highly respected author and physicist Paul Davies has an even more bizarre idea. He suggests that the strangeness of the measurement problem can actually explain how the universe came into being.
The experimenter today in the lab can make a measurement which will affect the nature of reality as it was, say, 5 billion years ago. And I think there's a sort of feedback loop between the existence of living organisms and observers and the laws and conditions which have given rise to them, because otherwise it just seems a bit miraculous that the universe happens to have started out with the right laws and the right conditions that will lead to observers like ourselves who are able to not only make measurements but make sense of it all. But quantum mechanics provides just such a feedback through time, because it does allow this backwards in time effect, not backwards in time causation. It's not that we here now can do things to change the past, to fix it up so that we can be sure we exist, but we have an influence on the past through the quantum measurements we make today.
But there's a pragmatic side to the debate too. Other scientists are worried that these bizarre and metaphysical speculations leave the world of measurement and laboratory experiment far behind. Professor Andrew Jackson of the Niels Bohr Institute in Copenhagen says that ultimately we shouldn't worry about the interpretation or the measurement problem or the cat. He says we shouldn't be concerned about the so-called true nature of reality. It's enough that the theory works.
All of the things we can measure give us questions that we can answer from quantum mechanics. So that the quantum mechanics itself, without the need for an interpretation, as far as I know, provides us with answers to or predictions regarding the result of every experiment we can do. So I don't know, and that's enough for me.
Yeah. So you don't think quantum mechanics needs a unique interpretation because it doesn't add anything?
It doesn't add anything, and I don't think it's going to lead us to the next step. And the whole point of an interpretation is it doesn't change the results or the rules of quantum mechanics. And that's why it's not testable. I mean, the whole purpose of the last 200 years in physics, this incredible leap forward that we've made, has come because experiment confronted theory and led to new theory when theory broke down, and then back and forth, the crucial experiment, the new theory. Interpretations don't do that. Interpretations only give us some kind of a way of believing to understand what quantum mechanics tells us, but that's a fixed point. But there's no new content interpretations.
Quantum mechanics is counterintuitive and sort of goes against common sense. What do you say to people who insist on wanting to know what an atom is doing when you're not looking at it?
I'm not sure who I'm quoting. Some people say it's Feynman, some people say it's Dirac, but the answer is shut up and calculate.
So your bottom line is shut up and use the maths, right?
Right.
Shut up and calculate? Is this really scientific pragmatism or just dogmatic fundamentalism?
The reason that this is unacceptable philosophically can be best understood by comparing it with an earlier episode in the history of physics, namely the Inquisition's attitude several hundred years ago to the idea that the Earth goes around the Sun instead of the Sun going around the Earth. They wanted to promote a compromise with Galileo where they would admit that the positions of the stars and planets and Sun in the sky are exactly as predicted by that theory, but that it was presumptuous of humans to purport to be able to describe the underlying reality, why the stars appeared in one place rather than another. Same thing happened with